Hello, and welcome back to Beyond Networks, the evolution of living systems. Last time, we were looking at evolutionary novelty, which was defined as the appearance of a new structure, a new trait that is not homologous to any other structure in the same organism or some structure in an ancestor. Today, we're going to shift focus to the second aspect of innovation, new functions that arise in evolution. And we want to talk about what is it to capture the truly open-ended nature of evolution. And for that, we need to revisit Lee Smolin's idea of doing physics in a box. Remember what he called the Newtonian Paradigm. And Smolin was pointing out that to formalize a physical system, we need to first isolate it from the rest of the universe. That is drawing the box, distinguishing the system from its environment. We then can specify the rules of change, as well as the initial and the boundary conditions that apply in this particular box. And if we do this, we can predict the trajectory, that is the future evolution or history of the system. And since the configuration space of the system remains fixed in this case, there is no true emergence, no new rules or configurations in such systems. Think about that. So everything that is possible is pre-given in this approach. Okay? Newton adopted the physics in a box approach to the whole universe and everything in it. And Lee Smolin, the main aim of his work is to criticize that. But there are problems if you look at smaller systems, not the whole universe, organisms. And of course, also the process of evolution has problems with this concept, because undoubtedly, evolution is the creative process that generates new, truly new sort of states in the world that the world has never seen before. So we will have to examine in this lecture, what does it mean to really radically innovate like this? And what are the kind of scientific tools we need to study it? This sort of physics in a box view of Newton leads, of course, to the view of the universe as a mechanism, as some sort of machine. And that leads us straight to Laplace's daemon. We've come across him already. This daemon was imagined by Pierre-Simon Laplace to be omniscient. I'm showing you a beautiful drawing here by Richard Soleil. And so the daemon knows everything about the current state of the universe. Everything about the rules that govern the universe. So it knows the initial, the boundary conditions, and the rules, the laws of physics. And because it knows that, it knows everything, not only about the future, but also about the past of the universe. So this is a strong form of determinism, Laplacian determinism, that is often seen as the ideal approach for especially physics, but also other sciences. If we would only understand the rules that govern the universe well enough, we would understand everything about the universe. Okay, there's a very strong sort of philosophy behind this, which was pointed out by Stuart Kauffman in his book, Investigations, but then more explicitly even in a follow-up paper in 2014 in Biosystems. So he is saying, Stuart is saying, in this view, in this Newtonian paradigm, becoming is entirely entailed by the laws plus initial and boundary conditions. So becoming is sort of the evolution of the universe, evolution itself, biological evolution, and entailed means the laws logically determine what can happen, okay? As I told you last time, in such a universe, there is no new thing under the sun. Take a quote from the Bible. And the reason for this is the future is determined by the laws of the universe. There can be no true innovation. But this is a bit of a paradox. This is not how the world really works, right? So one problem is, as Stuart points out in his investigations book, is that the universe lives in a space of possibilities, a configuration space that is stupendously enormous. It's humongous, okay? And so history is a quasi random walk in this absolutely huge space of possibilities. So I'm trying to show you here with this movie. So what does it mean for the universe to be non-ergodic? So this is the first aspect that should make us worry about this Laplacian view. If the universe were ergodic, that simply means that history could sample all equally sized subvolumes of the configuration space with equal probability. So basically, if we wait long enough, the universe is going to visit all kinds of possibilities with equal probability. And therefore, what we know about the universe would not be history dependent. Unfortunately, if this space is so large, the universe becomes non-ergodic. Configuration space is so tremendously large that history would never have enough time to sample configuration space evenly. Okay, so we cannot simply use statistical methods to infer things about the universe. So here is an example, also from Kaufman's book. So imagine how long it would take to make all possible proteins that are 200 amino acids long. And we can calculate through this, right? Because we know how many possibilities there are. There are 20 amino acids. So for each position, 200 positions, we have 20 possibilities. So it's 20 to the 200th, which is about 10 to the 260th. This is an absolutely unimaginably large number. Just compare this to the estimated number of particles in the known universe, which is just about 10 to the 80th, plus minus a few orders of magnitude. Thus, we can infer that there could be at most this number squared, right, of bimolecular reactions at any given instant. But everybody would react with everybody else, right? We would have 10 to the 160th bimolecular reactions at each moment. Then further assume that a fast chemical reaction takes about a femtosecond, which is 10 to the minus 15th seconds. So the number of femtoseconds that have elapsed since the Big Bang is about 10 to the 33rd. And now you can calculate the number of bimolecular reactions that could have possibly happened in the universe. The most, in the best case, if everything is always reacting with everything else, you could 10 to the power of 193 bimolecular reactions so far, which is massively less than these possibilities. So you can conclude that it would take at least 10 to the power of 67 times the current age of the universe to make all possible proteins of length 200. And that, you know, is just a tiny sort of fraction of the space of the real possibility. So the history of the universe had very little time. It's sort of been stuck in a little corner of that huge configuration space. Stuart Kauffman calls this a kinetic trap. So he says the universe is kinetically trapped, historically, we could also say trapped in some tiny subregion of its configuration space. So we haven't seen anything yet. So where we are in this space depends crucially then on our entire history. Non-ergodic means non-repeatable. Okay, what the current state of the universe is radically history dependent because it is non-ergodic. And so we cannot know this full history in full detail. A lot of facts have been lost, and we are finite, limited human beings, which brings us back to Bill Wimsatt's view of a science for limited beings. And he starts his 2007 book with a beautiful chapter that's called The Myth of Laplacean Omniscience, where he writes that this idea of knowing the entire configuration space, drawing this box for the entire universe and knowing everything about its past and its future is an unobtainable goal, even in principle. The only being that could do this is some kind of God, unlimited being. Limited intelligences can't do this, so it's not even a good ideal for doing science, okay? So this is very important. So this view, this naive view that is behind the Newtonian paradigm and is still very strong today, is completely infeasible and unrealistic. So what can we do? How can we deal with this situation? And so if we can't sort of know about this huge configuration space, what can we do? This is not all of it. Actually, there are worse problems coming up right now. Okay, so it's not only that this configuration space is huge, there is also sort of a paradox in this idea that we could sort of predict the future. And this is pointed out in this beautiful book by Nicholas Rescher, Unknowability, which I highly recommend, where he talks about this paradox of if we could predict discoveries in detail in advance, then we could make them in advance. And why that is a paradox, we'll see in a little bit in this lecture. The exact same argument applies for innovations in the economy or in evolution. Let me make that a bit more clear with an example, which is again from Stuart Kauffman. Imagine you have a screwdriver and you're trying to determine what are the possible uses, functions of this screwdriver. Anything goes. Okay, so obviously it's good for fastening bolts, but there are tons of other possibilities. You could, pry it into a door to keep it open, et cetera, et cetera, et cetera. You can pick your nose with it. I don't know what you're going to do with it. But what you do with this screwdriver depends radically on its context, where and when it is in a specific history of the universe. This is exactly the consequence of the non-ergodic nature of the universe. And so basically, at every moment, there is radical diachronic emergence. So the universe enters into a new space, a new state that we cannot possibly predict. And that is meant by diachronic emergence. So that is an emergence over time. And of course, the word emergence means that what is coming out is not predictable in advance. Okay? So this is a very important concept and a very different view of the universe from the Newtonian view. It is a radically process-oriented open view. So you can imagine the universe being in a certain state, okay, in the space of possibilities. So the current state is the actual. It exists. It's not merely possible or potential. And so the actual state of the universe is moving on, as shown in this diagram. It went from here to here over time. So each actual state provides boundary conditions, which means a specific historical context, that serve as enabling constraints to generate the next actual state from adjacent possible opportunities. So basically, these are constraints on what's going to happen next because we're in a non-ergodic sort of little corner of the state space. And what is going to happen next, these adjacent possible opportunities, possibilities that are only one step away, completely depend on the current state of the universe. And they're regenerated at every step. These enabling constraints are radically rooted in the context, historical and present, everything else that happens in the universe of the current actual state. They cannot be prestated with any certainty before they become actual. Okay, so this is what is meant by radical emergence. It means that the rules and also the state of possibilities changes at every step in time. Part of the rules that govern the history of the universe, these enabling constraints, they emerge during every actualization of the next adjacent possible. So this is what Kauffman means by radical emergence. Evolution creates the very possibilities into which it becomes. The same applies, by the way, to the evolution of scientific knowledge. New insights define new questions that only emerge when you got to that certain state. Because as Rescher said, you cannot predict individual innovations or discoveries. The adjacent possible is not actual, but it is real in a weird sense. We'll come back to that because it influences the emergence of the next future actual. Okay, so Kauffman writes, the ever-growing adjacent possible non-causally determines what we become. I will challenge that. It's not a modern sort of idea of cause. It's not mechanistically, basically, that it determines, because it is a future possibility, but it influences what's going to happen next, okay? Because it determines the possibilities that you have at any given moment. So here you get a picture of open-ended evolution and radical emergence. Evolution is radical, ongoing co-creativity. It's Beautiful, okay? Context-dependent coevolution happens of states and their constraints. It goes hand in hand. There's a dialectic dynamic again, which we've seen already when we talked about the organization, the dynamic organization of organisms. And not only can't we predict future events, but often we can't even know what can happen. So we cannot even predict probabilities because we're lacking the proper distributions. Just from looking at the distributions of past events, we cannot predict the future. This is basically not just important for evolution, but it's the foundation, of course, of black swan theory by Nassim Taleb about how black swan events are events that are fundamentally unpredictable, that shape human history to a large degree. And they are unpredictable because we cannot derive their probability from probability distributions measured over past events. The universe is fundamentally unpredictable. And what evolution does is it deals with this unpredictability. And this is one of the main points of Taleb's work, is that we should make our societies much more anti-fragile, learning from unpredictable events like evolution does. So what's happening here is very un-Newtonian, okay? Configuration space, physics in a box, the configuration space was fixed, okay? All the different possibilities that we had, different configurations were fixed in advance, okay? So configuration spaces represent spaces of possibilities. And what's happening in Kaufman's model is that this space constantly emerges with each actualization from an adjacent possible. Constantly emerge, these new rules, constraints emerge constantly and change over time, which means that the configuration space, the space of possibilities itself, changes over time. It cannot be prestated, just like we cannot prestate all the possible functions of a screwdriver. This and the rest of the lecture, by the way, is beautiful work by philosopher of science Maël Monteville, and this particular paper that I cite here on this slide. So the problem is, the criticism of this view of Kaufman's is that couldn't you just define a larger space that incorporates all possibilities, those that emerge as well, okay? And then we're back to the Newtonian paradigm. It's a tremendous space, so it's not practically sort of feasible to look at it. But I want to convince you that it's not even in theory a good idea to look at the universe like it would have a fixed space of possibilities. It's a fundamentally wrong way to look at the world. And for this last part of the lecture, we have to take a little excursion to the world of Jorge Luis Borges. Remember him from the story about Orbis Tertius and Tlön and these people who didn't have any nouns in their language. So this story is called The Library of Babel, and it's a humongous, huge, infinite library made out of hexagonal rooms full of books. And this library contains all possible books that are made of combinations of 25 different characters. So 22 letters, the period, the comma, and the space. Okay, so it's infinite because it contains books of any sort of length. The books are arranged in a seemingly random and meaningless manner, okay? So there's no order that you could go and look for books in this library. And it is a fact that the library must contain somewhere every coherent book ever written by humanity. But even more, it must contain every coherent book that ever might be written by anyone using this alphabet, and every possible permutation or erroneous version of it as well. It's an amazing library. So, unfortunately, this library is huge, and meaningful books are really rare. In fact, they're infinitesimally rare in this infinite library. So they are unfindable, undiscoverable in this sea of meaningless gibberish. Okay, and so that is a problem. So we can pre-state the configuration space here, but the fraction of actually meaningful, relevant instances of books is so small that it doesn't help us at all to understand what they are about. Let's shift example, and we're going to come back to biology, don't worry, in a minute. So Maël uses the example of symphonies, okay? So we can define a space of all possible music scores based on the notation we have, the instrumentation of an orchestra. Let's say we keep that fixed, and there's a huge space of possible scores. Now we want to find the subspace that represents symphonies among these scores, just like looking for a book in the Library of Babel. And this is an example that goes back to the French philosopher Henri Bergson and his work on creative evolution. So he says, he makes a very strong statement and says, a symphony is not possible before it becomes real. What does he mean? So he says that if you would have a precise idea of the symphony in advance, that's the same as composing it. Again, just like Rescher said, if you could pre-think of a discovery that you're going to make, you would have already made it. If you can think of a symphony, you've already composed it. So there is an apparent paradox here. It is possible to pre-state the entire space of possible scores, but Bergson says, once you have the idea of a specific symphony, you have the symphony. Okay, so if you've conceived of the possibility of this symphony, you've already composed it. So what's going on? So the notion that all possible symphonies are preconceivable is absurd, Bergson says. Well, is it? Yes and no is the answer here. And this is sort of a really mind-bending argument. Okay, so Mayel notes that you can define a set of all possible music scores, which must contain all possible symphonies. Okay, so you can pre-state the whole set of possible scores. But defining the set does not mean that we can define the individual properties of the elements. Okay, so that's very important. What makes a symphony a symphony? Defining the space of all symphonies is not the same as defining all musically relevant symphonies. Okay? And that is really, really important. So it's like finding a meaningful book in the Library of Babel. And we can learn about this problem from stepping even a step further away from biology and looking at the definition of different types of numbers. What I'm showing you here are the different sets of numbers that mathematicians know about, from the natural to the integer that include the negative numbers, to the rational numbers, fractions, real algebraic numbers that can be expressed as square roots, etc., and transcendental real numbers like pi or Euler's number that never repeat and never end their digits, decimal digits. Okay, so let's look at this really bizarre set of all real numbers. It is easy, straightforward for a mathematician to precisely define what that set is, what kind of generic properties these real numbers have. But the interesting thing about these real numbers is that most of them cannot be defined precisely, especially those transcendental numbers. We don't have a way to define the precise value of pi because it's infinite after the decimal point. Okay, really weird stuff. So the real numbers that we can define are infinitesimally rare. Okay, just like the books in the library and the symphonies in this among the scores. But luckily, real numbers have many generic properties. You can say in general, for example, that the square of any real number is larger or equal to 0. Okay, and so on and so forth. So real numbers have many generic properties, so we can say a lot about them, even if we can't define them individually. Let's look now at the set of natural numbers. Okay. Here, again, it is straightforward to precisely define what the set is. 0, 1, 2, 3, and so on ad infinitum, okay? And also, it is straightforward to precisely define any individual natural number. You can count. If it's a very large number, you'll have to count for a long time. But there's no, in principle, reason why you couldn't do it. But again, since it's an infinite set, you cannot define all natural numbers because there are infinitely many. Okay, so there are always elements in this set that have never been individually defined and described because there are an infinite number of them, and as finite beings we cannot define them all. So symphonies, what are symphonies in this space? Think about it. Symphonies and also the books in the Library of Babel are like the natural numbers here. Okay, so they are definable individually. The set of all different symphonies is also definable. We can pre-state the set of all different music scores, but we cannot define all the different examples of symphonies, because the relevant properties that make an admissible symphony, a symphony that we would like to hear, those properties are not generic like the generic properties of numbers. They don't follow laws. What makes a symphony admissible, meaningful, is radically dependent on the context and changes over time. Okay, so here is the clue to why, even if we could pre-state all the different functions that something has in an economy or in biology, it wouldn't make any sense, because the actually relevant cases would be infinitely small and lost in this huge space of possibility. Okay, so back to Miles' argument. He says the set of all possible music scores only defines what he calls pre-possibilities, okay, because we cannot define any of the elements individually. Okay, so if we have just defined the whole set of scores as a set, but haven't defined any of its elements individually, then we have a set of pre-possibilities. We don't know what any of these individual elements are like at all. So making the individual properties of a symphony explicit means turning it into a real possibility, in the sense that the adjacent possible is real as well. We'll come back to that next time. Okay, so that's different from a pre-possibility, and it immediately means making the real possibility means it is a symphony, okay? Making those individual properties explicit, but that is very important, depends irreducibly on context, radically on the context you're in, okay? So what makes a song, a symphony, anything meaningful right now, a book meaningful, this lecture meaningful, depends on everything else in the universe and the entire history of it, in a very radical sense. Okay, so of course there are degrees of making properties generic or not, okay? But a lot of properties of individuals in such sets are not generalizable, and biology is full of them, okay? So a lot of the facts about biology, not just about symphonies, is radically context and history dependent. So Bergson wins because he's right. The possibility of a symphony does not pre-exist the symphony. That's from Miles' paper, of course, again. So he was right, but you can't pre-state all the music scores. So the same applies to the evolution of living systems. We can define the sequence space of all possible sequences of DNA base pairs. That's possible. But if we do that, the number of meaningful sequences is not only infinitely small, but also radically dependent on the context of the bearer of those sequences. Novelties are not just the appearance of novel patterns or structures like we covered in last lecture, but novelties are emergent enabling constraints in the sense of Kaufman's theory that must fit into the existing context, that is the organization and the environment of the organism. What that means is the topic of next lecture. So we have to revisit this theory, the organizational account of the organism. Remember the notion of constraints that came out of that, which is exactly the same as the constraints, the enabling constraints here. And then look at how organisms and the environment interact to understand what makes a novelty, an innovation in evolution, a true novelty, a true innovation, because it is a meaningful innovation. Okay, I hope you're going to tune in for that again next time. Thanks for listening. Bye-bye.